So yeah, right. Okay. So so any questions regarding the last lecture on like pipelining or single cycle design? Okay. So is this slide visible? Hello?
Yes, sir, it is visible.
Yeah, right. Okay. So if you don't have any doubts, so let's continue the this one, the class, the previous lecture. So in the last class, actually, when we are discussing about the pipelining concept, so we are seeing that how it is differing from the single cycle approach. And yeah, we are just discussing before going to the details of data path or controller required for a pipelining, for implementation of pipelining. And first, we are just discussing about the basic principle and the various issues, generic issues that are involved in the pipelining. So in that, one of them we have seen that control hazards. There are three types of issues that arise in the implementation of pipelining. Control hazards, that is because of the conflict in the using the resource by multiple instructions in the pipeline, and that you can able to resolve by providing sufficient number of resources so that there won't be any conflict in execution of instructions in the pipe that are present in the pipeline. And the next one is the data hazard. So in the data hazard, what we observed is that this is because mainly due to the dependency in the when you are executing instructions, if there is a dependency in the instructions in the sequence, then you need to face these data hazards. So it means that a particular instruction which requires the input that depends upon the previous instructions completion of execution. And in that case, we have a conflict, we have a problem in accessing the data by a current instruction because the previous instruction is not yet completed. So that's where the problem of data hazards will be there. And for resolving that, we have various issues. One thing is that so we need to stall the pipeline and let the previous instruction be completed, and then you can start the present instruction or the instruction which requires the data from the previous instruction. So that is one option, stalling the pipeline. Whenever the a particular execution of particular instruction needs the data from the previous instruction, outcome of a previous instruction, and if the data is not available, so in that case you need to stall the pipeline and then you wait for the data until the data is available. So because of that, the performance of the pipeline will be affected because the moment once you are stalling, so that particular instruction for which you are stalling the pipeline, that requires some more time. And not only that particular instruction, the following instructions also will be waiting in the pipeline without further movement and all. So that way, if these data hazards, frequency of data hazards, if they are more, so then the number of that means the particular instructions which are waiting in the pipeline, they needs more cycles for its completion and all. So that affects the performance of the efficiency of the system or performance of the system, overall system. So we try to see that as far as possible, try to minimize the stalls. So that way, one way to overcome this will be the forwarding or bypassing that we introduced in the last class. So here in the concept of forwarding or bypassing is nothing but, for example, these two instructions, whatever here illustrated here, add instruction, then followed by subtraction instruction. And here the add instruction, the result will be placed in S0 register. And whereas for performing the next instruction, subtract, in its execution stage, it requires that means that the output of the add is required for its execution and all. But the output will be available after one or two stages later on. That means here by this time this execution starts, so the S0 is not available in the register file. So, but actually its execution, the computation of S0 is over by the previous instruction by that time. So in that case, instead of in that case, you can go ahead and write into that one as per the normal instruction procedure. But at the same time, since already the output is computed, it's available in the previous instruction in the previous stage. then you can directly forward that into the instruction which requires in the present stage and all. So that way here, because in the previous stage between 400 to 600 nanoseconds or whatever in this time scale, suppose the previous stage computed S0, it's available by 600 at this time. And now this is required, the execution stage of the next instruction requires between 600 to 800. So in that case, you can able to directly forward that to the present instruction so that the present instruction can use this data input directly without fetching from without trying to fetch from the register file, because anyway the register file doesn't contains this result and all. So this is known to be forwarding. It means that directly it forwards the data to the following instruction. So it's known to be forwarding, and it's also known to be bypassing, because actually here the result is not written into the register file by this time. So we are bypassing that and we are directly feeding from the previous instruction itself. So that way it can be viewed as bypassing the stages where the result has to supposed to be passing through all these things, and then finally it has to be stored here, and the stored result has to be accessed in principle. But here we are not doing that one, so therefore we are bypassing all these stages. So we can also view it as a bypassing. So that way it is known to be either forwarding or bypassing way of overcoming the data hazards and all. Here in this context, you can able to avoid the stalls, or you can able to you can able to handle this situation using the concept of forwarding and all. But all the time the forwarding may not rescue the like situations and all. Like here, for example, if you look at the instruction sequence, for example, have a load instruction, then followed by the subtract instruction. So load instruction means you just fetch the data from a memory and placed in S0 register, and that S0 content has to be used by the following instruction, following arithmetic instruction. So here in this case, the forwarding will not help you, because you can see in the case of load instruction, the data is available not at the output of execution stage. The data is available because here the data has to be extracted from the memory and it has to be placed into the register file. That means the data is actually available only at the end of the memory stage. So the following instruction, if it follows as per the pipeline, it requires this data, whatever the outcome of this memory or S0, whatever to be there. So it is available here exactly the same stage only. But here to get the data from this one, then we need to backward in time. It means that wherever is required, by the time the data is not available. So it needs to put the backward. That backward cannot be done because backward means it's a past. That means by that time the result is not available at all. So therefore, here in this case of load and subtract sequence of the successive instructions are load followed by any arithmetic instruction, for example. That happens most of the times because we require that, because we will fetch the data from a memory, one of the arguments, maybe other argument may be there in the register, and then we need to perform some logical or any of the arithmetic operation. That happens in very regularly. So in that case, actually, even though the forwarding cannot rescue, cannot overcome the situation and all. Still, here in this case, if you want to handle the situation, still we need to stall the pipeline for one cycle, so that after that we can able to forward the data from a memory directly to the execution stage and all, right? So that way, in case of this specific known to be load use data hazard, it means that so load followed by any of the arithmetic instruction which requires the data from the load. That so in that case, actually here the pipeline has to be stalled for one cycle, so that the data will be at least available for forwarding for the current instruction and all. So that's what can't always avoid the stalls by forwarding. So if the value is not computed when it is needed, because it is required here in this slot, right? By that time, the data, the value is the data is not at all computed, right? So therefore, we need to wait for till the data is available. So the data is available at this point. So we have to wait for one cycle, so that in the next cycle, then this data is available. Then without forwarding, sorry, we can able to, by using a forwarding principle, you can able to feed that data into the execution stage. So otherwise, actually here, if you don't use this forwarding here, then in this case, actually here we need to stall for two cycles. We need to stall for 2 cycles. And another way of avoiding these stalls will be code scheduling. It means that if you can reorder the code, suppose this is the sequence of code, like if you are performing these two expressions in the high level language, A equals to B plus C and C equals to B plus F. And if you translate or if you can able to write the machine code for this, the MIPS code for this. So these are the sequence of statements, assuming that all the variables are available in the memory. So in that case, for performing this one, to get the B and E, so we had to use the two load instructions to fetch B and E. Then afterwards, you can perform add operation. And afterwards, again, A has to be placed in the memory bank. So you have to store that result into the A. So these four statements, the first four statements will be for this execution of the first statement. And for the second statement, already B is available. So we have to fetch the F. So therefore, again, we have to use one more load statement. Then afterwards, we need to perform addition of these two, and then we have to store it. So these are the sequence of statements, the MIPS code equivalent to for these two C statements for its execution. So when you perform, if you look at the sequence of this code here, again, this will result into the data hazards. Data hazard, because here, when you look at here, the load followed by, you can see the load followed by the arithmetic instruction. So it leads to like data hazard. And again, here also load followed by arithmetic. It's not just simply load followed by arithmetic instruction. What we need to see is that in case of load, what is the destination register? And in case of arithmetic register, what are the source operands? If this destination register in the load and the source operand in the add, if these two are conflict, if these two are same, so then in that case, the data hazard will be result. Otherwise, if the add will perform on some other like T1 and something else, for example, T1 and some T5, for example, then there won't be that hazard, right? So that way we have to check that when load and following the arithmetic instruction, and if these registers matches, then we have a conflict. Then we have the data hazard will be there. So here also we have a data hazard. So one way to avoid this data hazard will be here. If you can able to give one more instruction to be executed between the load and add, then by using a forwarding, we can able to avoid the stalls. By using forwarding, you can able to stalls. But here also, so that way here, if you can reorder this code simply just by like shifting this load statement, the third load statement here successively after this one, after the first two load statements, then if you place the remaining code as it is, then there won't be any stalls at all. There won't be, and there is no need for any stalls, and you can able to execute the program without that. That means that we can able to, here still you may require the forwarding is required here and all, because the load and afterwards there is one more load is there. So by this time, the next add when it comes, by that time, here the add will be in execution stage and this load will be in the load is in the completion of memory stage. So therefore the data is available, you can able to forward it. But for the second one, even that is also not required. It is safely available. The T4 is available in the register file itself, because there are two instructions were there in between. So by that time, the T4 will write into the register file and can safely take the contents from the register file itself. Here, while execution of this one, for the initial sequence without any reordering the code, it requires 13 cycles, but normal execution requires 11 cycles. Normal, because the pipeline is 5 stages, right? And if you feed the instruction into that, after 5 stages only, the pipeline will give you the result. So the completion of all these, like for example, the 7 instructions, you require 7 plus 4. 7 plus 4 cycles are required, right? Because when you enter this one in the 7 cycles, you can able to feed all the 7 instructions into the pipeline, and after you feed that one, you require the last instruction requires another 4 cycles, So therefore, total 11 cycles are required. But here, what happens because of these stalls? Because of this one, the load followed by arithmetic instruction, it requires, even though if you use the forwarding idea also, but still requires 1 cycle to be stalled here and here also. There were 2 additional cycles that are required for execution of this one. So total 13 cycles are required using the forwarding thing. And whereas here by reordering the code and all, it requires only 11 cycles. It requires 11 cycles. So that way you can avoid the data hazards by by using the code scheduling, and this can be done by the by a compiler can be done can be take care of while execution of the while translating the data high level language instructions into machine instructions, and it can able to check that actually the sequence of machine instructions, and if there is any match kind of a thing, then if possible, then it can able to reschedule, it can able to reorder the instructions, so that at the same time you have to perform the reordering such that actually here the end result should not be changed. So because of that, the stalls will not be there, and the performance of the pipeline implementation will be reached to its maximal, its ideal case. Uh, Then coming to the other category of issues are known to be control hazards in the pipelining. And here, as we know that these control hazards arises due to the branch instructions. In a normal case, the pipeline, the instructions will be fed into the pipeline successively, like the PC, PC+4, and then so on. It just fetches the instructions in a sequential way. It means that the PC will be updated sequentially by incrementing the its address by 4. So therefore, each time the successive instructions will be fetched. But as we aware that in case of a branch instruction, where the next instruction to be executed, that depending upon the branch result. The branch result. That means there will be some condition will be validated, and based on the result of a condition, the next instruction to be executed depends. Suppose if the branch is taken, that means suppose if the instructions branch are equal. So if the arguments, whatever the register contains, if they are equal, so in that case, the address to be the next instruction to be executed, not the following instruction, not the immediate instruction. It will be somewhere else, which is indicated by the branch address and all. So in that case, we have the issues, like in case of when you're executing a branch instruction. So it may arise the hazards. It may arise the hazards because of the due to the feeding the wrong instruction to the pipeline and all may happens, right? And because here the branch result, maybe we don't know whether it may be correct or not. If it is not correct, then no problem. Because anyway it has to it has to take the following instruction. But if it's wrong, but if it is correct, then the instruction to be fed into the pipeline will be different, right? So that's where we have a problems in execution of these control statements. So that arises the issues in the pipeline. So we need to see that how do we avoid or how do we minimize these hazards and all. So one way in case of MIPS pipeline, the way this branch instruction will be executed, we are already aware of that. We need to compare the register arguments, and then along with that, we also compare the branch target also. Then based on the comparison output, whether the next instruction will be based on the branch target or the immediate the following instruction. That depends upon the branch result and all. And here, suppose, but here to perform this branch instruction, we require, that means for knowing about the comparison operation, then the branch calculation and all, it is usually happen in the third stage. And again, the result will be available in the fourth stage and all. The result of the branch is available in the fourth stage. So it means that in case when you're executing a branch instruction, so because the result will be happens or takes place after the results will be known, the comparison will be done at the third stage, but the result will be taken at the fourth stage. So therefore, for knowing about the branch result, so we need to wait till that the branch instruction has to pass to the fourth stage. So by that time, the 3 more instructions will be entered into the pipeline. 3 more instructions will be entered into the pipeline. Suppose if the branch result is true, for example, it means the condition is true, then the next instruction to be fed, the actual instructions sequence to be fed will be based on the branch target address. But already the 3 instructions, the successive instructions already fed into the memory, fed into the pipeline. So therefore, here in this case, we need to remove these instructions, or that is not to be flushing out the pipeline, or we have to clean up the pipeline, the previous stages of the branch instruction, and we need to feed the correct instruction into the pipeline and all. So that will be the overhead, or that is the problem with the execution of branch instruction and all. So here in this case, one solution is that somewhat reducing the improving the performance will be, because here if you see that if the branch result will be available at the fourth stage, three instructions are already fed into that one. And the next instruction to be fed, for doing that one, you have to remove these instructions, you have to fed the new instruction, right? So it means that there are three cycles will be going to be wasted and all. That means for every branch instruction, if the branch taken is correct, if the condition is correct, then whatever the instructions that are feeding soon after the branch instruction, so that they need to be flushed out. They need to be flushed out. So here in this case, there are already three instructions are fed into the pipeline. So it means that these three pipeline stages, they will be like remains empty. So it means that you are wasting three cycles when you are performing a branch instruction, in case if the branch is correct, right? If the branch is not incorrect, then whatever happens, then whatever those three instructions, they will follow in a normal process. There won't be any issue at all, right? So to avoid this, or to minimize this loss, one can do that actually. Instead of knowing the branch result at the fourth stage, suppose if we can able to accommodate by using some additional hardware, and if we can able to do it in the second stage itself, because in the second, anyway, first stage we can't do anything, but in the second stage, because the instruction decoding can happen there, so with that you can come to know that it's a branch instruction. Then if you can able to do the requirements of branch instruction, that means the target address calculation, performing a comparison, and if you do all these things in the instruction decoding stage itself, if you can able to accommodate that, then the branch result will be known in the second stage itself. So with that, at least the loss can be reduced. Instead of three cycles, here the loss can be reduced to one cycle. Because anyway, till decoding, we don't know about the branch address and all, right? So therefore, anyway, by that time, when this branch instruction go into the decoding stage, it's second stage, there will be something else in the first stage, right? Or the first stage should be empty, or there will be by the pipeline principle, the immediate instruction has to be fed into the pipeline in the first stage. And here, based on the branch result and all, you need to flush out only that particular instruction. That we need not execute, we need not forward that whatever the fetch instruction. In place of that, the correct instruction has to be fetched in case if the branch is taken is correct. That means if the condition is correct, then the proper instruction has to be fed into that. Otherwise, the instruction can be continued. So with that, what happens is if you put some additional hardware in the ID stage, then the branch delay can be reduced. That means instead of knowing the branch result and feeding that, earlier it requires three cycles. Three instructions already enter into the pipeline. Now, in place of that, only one instruction is entered into the pipeline, and that has to be flushed out in case if the branch suggests the other address and all. Okay, so that way you can you can able to minimize the issues related to the branch target one way. So you can see this one actually here, the stall and the branch. It means that here if you look at here, that means there is a branch equal. That means this particular instruction, if it's execution. And here, suppose if you accommodate if you put the hardware into it and all, then still the branch to knowing about whether the branch taken or not, that requires again we need to know only in the second cycle of a branch and all. So during that time, whatever the instruction you fed into this one, so it has to be wait. So it has to be wait, or it has to be thrown out. So that depends. So therefore, in this case, at least we had to stall the pipeline by one cycle and all. That means the desired instruction to be executed, we have to wait for 400 picoseconds. Whereas earlier in the normal pipeline, for every 200 picoseconds, the next instruction will be fed into the pipeline. But here, if you can, in case of branch instruction, and if the condition is true, in that case, the address to be fetched will be depending upon the target address. So for that, actually here we need to wait for the completion of the branch, knowing the branch result and all. So therefore, the target instruction to be fed into the pipeline has to be wait for 400 picoseconds instead of 200, because the other 200 is because of knowing for the branch address and all, right? And suppose if you feed the next instruction and if the branch taken is not correct, then this bubble will not be there because anyway the branch address is wrong. So therefore the instruction to be fed will be anyway the next instruction only, the following instruction. So therefore that can be executed. But if the branch taken is correct, so in that case the address to be fetched, the instruction to be fetched depending upon the target address. So therefore at that time whatever the immediate instruction that is fetched, the next instruction that is fetched, that has to be flushed out. It means that in place of that again one more instruction has to be fetched. So therefore that particular cycle will be wasted, right? So that will be result in the remaining all pipeline stages also that follows. Because the pipeline, the instructions will be follows in a sequentially. If one stage will be idle at a particular time slot, and that bubble or that idle that one has to be carried out, that has to be moved forward till end of the pipeline. So therefore, you can able to see that here the bubbles are represented in each pipeline stage from the wherever the instruction has to be stalled. Okay, so this is about the branch instructions. And here, yeah, but here how to avoid these stalls? Because for example, as we know that for certain programs, the branching frequency is somewhat reasonable. It's about there is some particular data set where there are more frequent branches used to be there. And if you analyze that particular data sets, you can see that the programs that are related to that, you can see that there are about 17% of the instructions are the branch instructions. So it means that actually for every branch instruction, if you use by this method, the previous method, like whenever the branch instruction arises, you need to stall for at least for one cycle and all. So if the frequency of the instruction is 17%, then the overall performance will be affected, delayed by the 17%. Suppose, for example, if there is no branch instructions, then all instructions will be executed successively for every pipeline slot, right? And whereas if the branch instructions are about 17%, that means for every branch instruction, we need to wait. That means one pipeline stage or one pipeline slot, one clock cycle will be additional is required for every branch instruction. So that way, earlier, if it is one ideal case, if it is one, and now it requires about 1.17, right? Because 17% of the instructions are branch instruction. For every instruction, it requires one additional cycle, right? So because of that, the performance will be affected. And the same thing here, this is the ideal one. This is ideal one means actually here you can able to accommodate this branch decision only in the decoding. You cannot move forward, right? So, but if the branches are delayed, that means if the decision is taken at the fourth stage or fifth stage, for example, if it is a long pipelines, that means in case of now the recent pipelines where the pipeline length is more. So if the branch decision is taken at a later stage, for example, at a fourth stage or fifth stage, then you can see that how much the penalty you need to incur. That means for every branch instruction, suppose if this branch calculation, if it takes at the fourth stage, for example, third stage, and the result is available at fourth stage, so it means that for every branch instruction, we need to pay a penalty of 3 cycles. Earlier and all here only one cycle. If you make the branch detection in the second stage, in the instruction decoding stage, you need to have penalty of only one cycle. But if the branch decision is taken at later stages in a normal way, like so, then at the fourth stage or fifth stage, then you need to stall the pipeline that many cycles and all. That means for every branch instruction, you need to have the penalty of that many cycles and all. So that's a problem with the longer pipelines and all. And but here also there are issues by keeping entire hardware in the instruction decoding stage, right? Because here every clock cycle should be all the clock cycles, all the pipeline stages are properly balanced. Otherwise, again, there is insufficiency in the implementation and all, right? So there are like trade-offs are there. And here, how to avoid even this stall also, one cycle stall, right? So that you can able to do it by using the branch prediction. It means that whenever the branch instruction is there, you can able to predict the address, whether the branch is taken or not, right? If the branch is not taken, for example, then the following instruction will be fed. If the branch is taken, suppose you predict that you will this particular instruction takes the branch, it means that the target address will be not the immediate instruction, it will be something else. If it is taken, branch taken, if it is if you predict that one, then you need to feed that address. You need to provide that branch address in the instruction fetch stage itself. So with that, if you can able to do that somehow, then you can able to avoid that stalling. You can able to avoid that stall. It means that in the prediction, in the instruction fetch stage itself, you have to predict by using appropriate hardware. You need to predict whether this particular instruction will be will take the branch or will not take the branch, right? So based on that, if it is not taking the branch and all, if you predict that actually if it not take the branch, then anyway the next instruction fed will be PC plus 4. Suppose if you predict that it will take the branch, then whatever the appropriate target address, branch target address, that should be available in the instruction fetch stage itself, and you have to provide that particular target address for in place of PC plus 4 in the next stage, in the following stage, so that you can able to avoid the stalls. And for doing this one, again, the prediction should be accurate, more accurate. If the prediction is perfect or the prediction is more accurate, so in that case, even though you can able to put some additional hardware or for prediction at the first stage itself, and you can avoid the stalls. Suppose if the prediction is wrong, for example, then you have to pay the penalty. The prediction is wrong, then we'll come to know about the branch actual target address, which is different from this one. So at that time, again, you have to pay the penalty. You have to pay the penalty means, again, whatever the cycles, whatever the instructions that are fed into this one wrongly, so they have to be flushed out, and the proper instruction has to be again replaced, has to be placed into the pipeline and all. But this can be taken if the accuracy of prediction is high. That means when you're predicting the branches, if you are 90% or 95% of the times you are correct, that means your prediction is true, then only 5% of the times you need to pay the penalty, right? So therefore, when you are going for a branch prediction, so we need to see that the prediction accuracy, if it is high, then you can able to accommodate that additional hardware, additional complexity into the pipelining and all. Yeah, that's what the longer pipelines cannot be readily determine the branch outcome, as I mentioned that. So therefore, the stall penalty will be unacceptable, right? At least if you predict if you can able to detect the branch in the second stage by providing additional hardware, we'll see that one later on. Then at least only one instruction will be maybe, if at all, can be entered into the pipeline, and that need to be flushed out. Otherwise, in case of longer pipelines where the branch detection will be done at somewhat later stage, and maybe at the third stage or fourth stage or so. So when the prediction, when this branch detection will be late, by that time the instructions that already fed into the pipeline, they need to be flushed out in case if the decision is other way. So that way you need to pay the penalty in case of longer pipelines and all. So therefore the prediction is better. So the predict means actually here the predict can able to predict outcome of branch. That way you can avoid the stalls. And here the problem is, if the prediction is wrong, then we need to stall. Then we need to stall means whenever we come to know that the prediction is wrong, at that time, whatever the instructions that are fed into the pipeline with this wrong prediction, they have to be flushed out, right? And the correct instruction has to be re-entered and will be placed into the pipeline properly. So that is a penalty in case if the prediction is wrong. As long as the prediction is correct, then there won't be any problem at all. So for that, we need to ensure that the branch prediction should be as accurate as possible, right? So yeah, in the case of MIPS pipeline, generally it predicts that the branch is not taken. The branch is not taken. That is one style of prediction will be always the branch is not taken. So what it means? It means that always take the next instruction. Just forget about the whether it's a branch address or whatever and all. You just go by normal sequence. That means soon after the branch instruction, whatever is there, that you can able to enter it, place it to the pipeline. So that is one way of predicting. That means always always assume that the branches are not taken, so that you can take the next instruction, following instruction into that. And otherwise they fetch the instruction after the branch, that with no delay. Yeah, this is the way, one way of predicting the branches and all. It means that always assume that the branches are not taken, predict that branches are not taken. So in that case, the following instructions will be entered into the pipeline, and then they will be allowed or not. That depends upon whenever you will get a branch result. At that time, you can able to come to know that. Okay, so yeah, this is just illustration of actually when the branch, when you make a guess, like for example, suppose when you go by normal guess, like branch not taken. So in that case, actually here what you are doing after branch instruction, immediately you fed the load instruction, that following instruction into the pipeline, and it will be executed. And here your prediction is correct. Branch not taken is correct. So therefore, the instruction whatever loaded into the pipeline after the branch instruction, so that can smoothly execute it. There won't be any stalls, nothing. But here, if the prediction is incorrect, that means you are executing a branch instruction, but you are entering the load instruction wrongly into that. You are entering because since it is the next instruction, you are entering into that one, assuming that branch is not taken. But in the second stage, you will come to know that branch is taken. So therefore, here that load instruction, whatever is executed, that has to be stopped, that has to be stalled. And in place of that, the proper address, the proper instruction at the address, whatever here the OR instruction, for example, that has to be fed. So for doing that one cycle will be wasted, and the proper instruction will be fed after this one 400 picoseconds. Right? 400 means anyway the previous instruction is fed after 200, and now it is again 200 will take. So therefore it takes 400 from the branch instruction and all. So here the stall will be, that means the pipeline will be stalled here, or you can say that you flush out the previous instruction and place the right instruction into that one. And since you stop the instruction, frozen instruction for one clock cycle, and that bubble has to be passed to all the remaining stages and all. So this is in case if the branch is incorrect. If the branch is correct, then there won't be any penalty at all. So therefore, this way you can, when you are predicting, so when the prediction is correct, then there won't be any stall at all, and the pipeline will execute in ideal way. And if there is a prediction is incorrect, then we have a problem. Then we need to stall or we need to flush out the instructions, whatever that are wrongly entered into the pipeline. And the more realistic branch prediction, like here, as I mentioned, that how you ensure that the prediction is correct most of the times, right? So there are two types of prediction. One is to be static prediction, other is going to be dynamic prediction. So in case of static prediction, as I mentioned that based on the typical branch behavior, we need to make a decision. It means that suppose for example, in case of loop statements or if else statements, where you need to check the condition and then afterwards you need to take a decision, right? You need to whether the branch has to be taken or not taken and all. So usually in case of loops, the decision will be taken at the end of the loop. At the end of the loop, that means you have a loop and then you have the statements will be there. And then when you reach to the last statement, in case of machine language, you will come to know, you will check the loop condition, whether the number of iterations are completed or not. If it is not, then again you have to go back to the initial statement and again you have to execute the loop, right? And so whereas if else and all, you have to check there at that particular statement itself. In case of if else statement, like if statement, where the condition has to be checked in that statement itself. Whereas in case of a loop and all, we have some set of instructions will be executed, and those has to be repeated till the loop, till the number of iterations have to be completed. And the number of iterations will be checked at the among the set of the instruction. The last instruction is the one where the check condition where the iterations will be checked. So therefore, whenever the loop is executing, at that time the branch is if it is related to the loop statement, then you always consider as a branch is taken, because here the multiple iterations has to be taken place. So therefore, you can safely take a decision as always the branch is taken and all, right? But happens that here when you come to the last iteration, at that time when you are trying to when you are making a decision, at that time you may go wrong, right? But most of the time the remaining 9 iterations, for example, suppose we go for 10 iterations, 9 times it will be correct. Only one time it will go wrong, right? And similarly, when you go for the in case of if else statement, because we need to, there is nothing like iteration and all. Here you can take the statement. Here you can guess that you can make a decision. You can predict that always the branch is not taken. So this is the static branch behavior. That means we are not bothering about what are the previous branches or whatever. We don't take any history or nothing at all. just by looking at the branch statement, if the branch is under the loop or if the branch is simply if else, then you just make a decision, you take a decision and all, whether the branch will be taken or not taken and all. If it is taken, then you need to provide the what is the branch address, because we know that in case of loop, all the time the branch will go to the again the loop beginning and all. So somehow if you can able to keep that particular address in somewhere, and if you predict that always the branch is taken, then instead of PC plus 4, you have to place that particular address into the PC. Otherwise, we have to go by the PC plus 4, right? So this is not to be static branch prediction. It means that just you blindly just predict that based on the statement like if or loop statement. Based on that, you need to predict that whether the branches are taken or not taken directly. And the dynamic branch prediction is a clever one, where here we have some hardware, and that hardware will measure the branch behavior and all. This particularly here, this hardware will just maintain the history of the branches, the previous branches, and then based on that, it tries to predict the future behavior and all, future behavior. So whether to continue the trend or not. So that depends upon the previous history and all. So for this, it makes use of some additional hardware, and then with that additional hardware, it just check that branch whether the present branch can be taken or not taken and all. And if it is a penalty, then you have to stall and then you have to refetch the desired one and all. And again, if there is a penalty, and then you have to update the history also. That means for every branch, you need to update the history, whether the previous branch is taken or not, and how many branches were taken and how many were not taken. And not only that one, the local one, even the because the local one means suppose you are executing some the loop statement, then the branches will be continuously occur, right? And then along with that in the program, there will be some earlier branches also might have taken and all. So therefore, altogether is going to be the global history. And the local one means the recently the branches, how frequently they're happening, that is going to be local history and all. So there will be hardware which used to monitor both the local and the global history of the branches. And based on that, it predicts the present branch, whether taken or not taken. If it is taken, then the address to be provided and all. So this is going to be dynamic branch prediction. We'll see the details of the static and dynamic branch prediction later, more detailed way. This is just to introduce how do we avoid the penalty due to the branch instructions. Okay, then coming to the summary of pipeline, whatever. So far, actually, we discussed about at a very gross level how the single cycle instructions or single cycle data path or single cycle concept can be used in a pipeline, where the single cycle can be splitted into the multiple stages and all. Like we know that the instruction will be executed in the different stages, like fetching, decoding, then execution, then memory access, then finally write back. So that way, if you can able to arrange the total execution in the form of different stages, and then you can incorporate the pipelining concept where we can run the multiple instructions where each instruction will make use of a different stage, a separate stage. And so we have seen that the pipeline improves the performance by increasing the instruction throughput. As we have seen that the performance depends upon the instruction throughput. And yeah, it executes the multiple instructions in parallel, each instruction, but each instruction will take the same latency. It means that the latency means the instruction execution time remains same. All instructions will take the same amount of time. But as the throughput increases, we are enhancing the throughput, almost like we are feeding the instruction for every whatever the pipeline stage duration. So therefore, we can able to see that much improvement in the performance and all. But when you are using this pipeline implementation, you have some issues will be there because of these various issues like structural hazards, data and control hazards that we have gone through that. What are those, and what are the techniques, or what are the ways to overcome that or reduce the effect of that, or for improving the pipeline efficiency that we have seen. And we also can able to observe that the pipeline implementation depends upon the instruction set, what the instruction set consists of, how the instruction set will be. Like because whatever the hardware that has to implement the instruction set, like instructions that are present in the machine level instruction set and all. So if the instruction set is proper, that means if it is a regular, and then if it is limited number of instructions and whatever the MIP supports, then the implementation of pipeline will be easier and all. Otherwise, it becomes very complicated and all. So the pipeline implementation, complexity of pipeline implementation indirectly depends on the instruction set architecture and all. It's nothing but the set of instructions it consists of. Like as we mentioned, in case of MIPS, it supports a lot by having its regular structure, having all instructions will be 32 bits and all. And in that instructions also, the fields will be like mostly it will be regular. They follow in the regular structure and all. Limited number of formats. So all these things will enhance the simplicity of the design of the pipeline in view of MIPS architecture. Yeah, now we'll just look into the, after knowing the broader details about the pipeline and its effects, various issues in that. Now we'll see that how to design a pipeline processor. Like earlier we had designed a processor with a simple way of implementation using known to be single cycle approach. It means that all instructions will be executed in only one cycle, but instructions will be executed in sequence. After completion of the previous instruction, the next instruction will start. So that way the entire pipeline will be occupied by the instruction all the time. Suppose if the instruction is fetched from the memory until its completion, the entire pipeline will be busy or entire pipeline will be occupied with that instruction only. So that is the basic concept of the single cycle approach. But each data path requires only a finite amount of time, only small amount of time to perform its job. But still, as long as the instruction execution takes place, completion, till that, the entire pipeline or all the components or all the data path components of the pipeline, data path components of the components of data path, all will be engaged with that particular instruction itself. And whereas in case of pipeline, we are deviating from that. In case of pipeline, what we are thinking is that you can assume that instruction will be executed through these 5 stages and all. And then you can effectively use these 5 stages like effectively by using the multiple instructions and all. Like for example, when you fetch the one instruction here, after fetching this instruction, then we pass the instruction to the decoding stage. At that time, this fetching unit can be fetch the next instruction and all. And when it's decoding, once decoding is completed and register operands are fed or read, and they will be passed to the next stage. At that time, the decoding stage is free. Then the previous instruction, whatever fetched, that can be passed to the decoding stage. So likewise here, in case of pipelining, we are making use of these various stages of a pipeline effectively by running the multiple instructions parallelly and all. Right? That means parallel means we are passing the instructions serially into the stages. Like each stage will be engaged all the time. Like in every clock cycle, like you can say that one stage will be operated for a particular instruction. Next clock cycle, the same stage will be execute the next instruction and all. So that way here, if you look at so that way this pipeline concept will improve the efficiency compared to the single cycle approach. But here, if you look at that, the pipeline is nothing but actually we are using the same data path, but we are cleverly using the data path instead of engaging the entire data path for a single instruction. We have split the data path into like different stages, and then we are allowing the instruction to pass through these stages, not only one instruction, multiple instructions in a serial way. That means at any point of a time, each stage will experience one instruction, new instruction. So that way, like these data path components also will be busy, will be effectively utilized over entire time, and the instruction throughput is also increases and all. Earlier, the instruction throughput will be after completing all these entire execution, then only the second instruction will be fed. But here it's not the case. The first instruction will be taken by fetching phase, and then it passed to the next stage. Then immediately the next instruction will be fed into that one. So therefore, here the throughput that depends upon the pipeline duration and all, whatever the pipeline duration. So with that time interval, each the sequence of instructions will be fed into the pipeline and all. And now we'll see that how do we'll prepare a data path. How do you design the data path for in case of for incorporating the pipelining concept and all. So for that, as we are seeing that the same data path we are using for a case of pipelining also. But the only variation here is that actually here we are using the stages individually for the individual instructions for different instructions and all. So it means that once the fetching is over, then whatever the information that is you achieved or you derived at the fetch stage, that you need to pass to the decoding stage. And now the fetch will be relieved, the fetch will be free from that, right? And likewise, in the decoding, when it's complete, decoding complete means here the decoding the decoder side the here maybe suppose we place a controller here, controller understands what these particular instruction, it derive the control signals, right? And afterwards it fetch the register operands, and these all this information that has to be passed to the next stage immediately, so that the decoder has to be free, right? The decoding stage to be free where it can be given to the next stage. So likewise here, whatever the information that is derived or that is available in that stage has to be smoothly passed to the next stage. So for that, how do we do that? That is the only task, additional task that is required in case of pipelining compared to the single cycle approach. Single cycle approach, there is no walls at all. Actually, there is no stages. We don't view that even though the instruction is executing all these stages, but we don't view this in the form of stages and all. It is, we will use this entire thing as a single monolithic circuit. So therefore, we'll view that the entire operation has to be completed in one cycle and all, in one cycle. But here we assume that this entire data path will be into 5 stages, and we try to segregate the operation of each pipeline stage so that the multiple instructions can run parallelly. So for that, actually here, whatever the outcome of this fetch stage, that has to be smoothly passed to next stage. Likewise, the stage 2 has to pass to stage 3 and so on. So for that, here there should be like for passing this information smoothly over the stages, we should have some storage is required. That means at the end of this cycle, one cycle, because we are assuming that all these pipelines, pipeline stages will perform its operation in one cycle, one clock cycle and all. So in the clock cycle, whatever the operation that has to be done, so that operation has to be passed to the next stage. So for doing that one, we need to have some storage is required where whatever happened in this clock cycle, so that has to be stored in a register or in some storage, and that information has to be passed to the next stage in the next clock cycle for the next clock cycle. So the same thing holds good for all the stages also. So therefore here, if you look at here, this particular data path, which is splitted in the form of various stages using these dotted lines. So if you place the registers over here at each of these vertical dotted lines, then the registers will hold the information about the state of the stage, the state of the stage during this clock cycle and all. And this state will be passed to the next stage safely, because this is a register or this is a storage element where it stores the details of the instruction fetch, whatever happened. It's nothing but the total instruction, and as well the increment of the PC also, the PC address which is incremented. Likewise here also, like in case of instruction decoding or register operands read and all. So the instruction, the contents of these two registers will be read, right? Because those addresses are available here and all. And then similarly here, suppose if the immediate address, the 16 bits are transformed to 32 bits, and they have to be passed on to the next stage. So all these, whatever the register operands and this immediate operand, whatever, all these things has to be again placed into a proper register or proper storage so that they can be used by the next stage. So the pipeline data path is nothing but a single cycle data path, just by introducing the registers in between the stages and all, so that the information will be properly percolated across the stages. So we'll stop here at this point, right? And next class on the Monday, we will continue this. And yeah. Okay, so if you have any questions, then we can go through that. Okay. So I'm stop. I'm stop recording. Yeah.